Good morning, this is Dr. Jingbo Louise Liu. Today we start your chapter 12, Intermolecular Forces, Liquids, Solids, and Phase Changes. In this chapter, we are going to give you an overview of the physical states and the phase changes, especially the solid, liquid, gas inter-exchange. And then we provide the quantification of the phase changes. For example, during the phase changes, the temperature will be maintained a constant. How do you calculate the heat which is transferred? And then we are going to show you different types of intermolecular forces. And then we are going to briefly discuss about the property of the liquid states, the uniqueness of the water related to its polarity, and 3 different phases. First of all, about the phase of matters. As we mentioned from a previous study, we already know you have 3 different phases. The phase of the matters normally related to its physical states. So these physical states of matter, you call it a phase, a physical distinct, homogeneous part of a system. The property of each phase can be determined by the balance between the potential and kinetic energy of the particles which is composed of that matter. The potential energy usually occurs in the form of attractive forces. This potential energy tends to draw the particles together. On the other hand, the kinetic energy associated with the motion, the movements of your particles, this kinetic energy tends to disperse your particles. Regarding the different forces, we can distinguish them into 2 types. One is called attraction, another one is called repulsion. The attractive forces normally involved in intramolecular forces and intermolecular forces. The intramolecular forces is also known as the bonding forces. The intramolecular forces are found within a molecule. The chemical behavior of each phase of the matter is the same because the same basic particles are present in each case. Your water molecules are present no matter whether your water is a liquid, your water is in a solid or gas phase. And the intermolecular forces is also known as non-bonding forces. These intermolecular forces can be found between molecules. Usually, the physical behavior of each phase of the matter is different because the strengths of these intermolecular phases are different from state to state. And your substances showed 3 phases, generally speaking. One is called solid, second liquid, third gas. These 3 phases can inter-exchange from one to another state. If your liquid becomes to your solid becomes to liquid, we consider this processing, this phase change, melting. Liquid to gas, vaporizing. And your liquid directly to the gas, we consider it sublimation. On the other hand, gas to liquid, condensation or condensing. Liquid to solid, called freezing or fusion. Gas two solid directly, you call the deposition. This second half changes in terms of the phases normally is the exothermic. The other part is the endothermic. During these different phase changes, so there is some heat is going to be transferred. The quantitative aspects of the phase changes can be denoted by two major processes. The first one, within a phase, such as just one phase, liquid, solid, or gas. Heat flow is accompanied by a change in temperature, since average kinetic energy of the particles change. This heat transfer can be calculated by this equation. Q equals the amount multiplied by the heat capacity multiplied by the temperature change. Usually this amount is the number of moles. This heat capacity called molar heat capacity. If you have a specific heat capacity, you need to know the grams. This temperature is the change in temperature. Therefore, the temperature change in Celsius and in Kelvin, they are identical. Second condition, during a phase change, the heat flow occurs at a constant temperature, meaning this temperature maintains constant as the average distance between the particles change. The heat flow can be calculated by the second equation. Q equals to the amount of delta H of the phase change. For example, from liquid to solid, you call it a fusion. Delta H will be the delta H for the fusion. For example, we have this diagram showing a cooling curve for the conversion of gaseous water to the solid water. Imagine you have your your water at temperature 130 Celsius. You keep cooling it down to a solid, which is -40. What's going to happen? You are going to see 5 different steps. Stage 1, your gas from 130 decrease temperature to 100 Celsius. This case you call the gas cooling. Whenever your temperature reaches 100 Celsius, you cooling it down. This stage 2 is called the gas-liquid phase change, also called condensation. During this condensation, your gas becomes liquid, temperature no change. This delta H is involved in the condensation. The third stage, whenever your temperature maintains at 100 Celsius, all the gas phase becomes to liquid phase. You continuously decrease the temperature. So the liquid from 100 Celsius will decrease its temperature to, 0 Celsius. At this case, everything maintains as a liquid. Your heat is going to be released from your liquid water at high temperature to the liquid water at low temperature. At 0 Celsius, what's going to happen? Your temperature maintains the same. At 0 Celsius, you are going to see the phase change from the liquid to solid. So in this case, you call it fusion. So this delta H represents the enthalpy change during the fusion. Whenever all the liquid becomes to solid, so you keep decreasing the temperature from 0 to -40. This is called solid cooling. So you can calculate stage 1, 2, 3, all the way to 5, the heat transferred. So the Q can be calculated using the previous equation, two equations. So we are going to show you one example. For example, so we have a question. We want to calculate how much heat is needed if you increase the temperature from liquid for your liquid water from 85 Celsius to 117 Celsius. So how do you find the heat of a phase change depicted by this molecular scene? In this case, you measured the water. You did the experiment using 24.3 grams of water. So what's your plan? So here is our plan. Step 1. You want to show your temperature change from 80 to 100, from 85 to 100 by your liquid increasing temperature, and then at 100 Celsius liquid becomes to gas, which is your vaporization. After you reach 100 Celsius, gas is going to be increasing its temperature. You have 1, 2, 3 steps. And then you are going to use related equation to do the calculation. But also you need to know the heat capacity for your liquid water, the heat capacity for your gas-phase water. You also need to know the delta H vaporization and the delta H in this case, you only need the delta H for vaporization. If you have that melting, you need to know another delta H. So our solution. So you are going to plot a graph. You plot a graph involved in 3 different stages. Stage 1, your liquid water heating in temperature increasing of your liquid. Stage 2, your phase change occurs from liquid to gas. You call it vaporization. Stage 3, your heating of the gas to the final temperature from, in this case, from 100 Celsius to 117. Our calculation of the heat. First of all, you want to determine the moles of your water. So you simply use the grams of water divided by its molar mass. My calculation is 1.35 moles of water. For stage 1, you use Q equals N, the moles, the amount, multiplied by the heat capacity for your liquid water, multiplied by the temperature change. The moles, which is 1.35, the liquid water has a heat capacity 75.4 joules per mole per Celsius. Your temperature change from 85 to 100, the difference is 15. 100 minus 85. So you can calculate the heat which required to increase the temperature from 85 to 100 Celsius. My calculation is 1527 joules, approximately 1.53 kilojoules. For your stage 2, this is called vaporization, your liquid to gas phase change. You use the Q equals to the moles of delta H of that phase change. In this case, is vaporization. N moles multiplied by delta H vaporization. This delta H vaporization, 40.7 kilojoules per mole. This number is already determined. The third stage is your gas temperature increasing. So the heat equals to the moles multiplied by the heat capacity for the gaseous phase water, for the steam, multiplied by the temperature change. The moles, again, still 1.35 moles. This is heat capacity for your gas water, for your steam, is 33.1 joules per mole per Celsius. Your temperature increase from 100 to 117, so which means you have temperature change 17 Celsius. So you calculated the heat which required for these 3 stages, and then you sum these 3 to calculate the total heat which involved in, so related to increased temperature from 85 to 117. So this is about the heat transfer during the phase change and during the temperature change. Followed by, I want to spend some time to discussing the phase diagrams for two different substances. The first one for carbon dioxide, the second one for water. First of all, what is the phase diagram? The phase diagram is a diagram. It's a schematic demonstration where you use pressure as your y-axis, your temperature change as your x-axis. In this diagram, you separated your diagram into three different regions to represent the solid, liquid, and gas. And also you have different phase lines and you have different points. This diagram is called phase diagram, particularly for carbon dioxide. So what we are going to see, as we mentioned, you have your solid, liquid, and gas three phases. So between this solid and gas, you see a curved down line. You see a curved line, curved down. And also between this liquid and the gas, you see another curved line. And then you also see a straight line between the solid and the liquid phase. This straight line has a positive slope. They have some meanings. And then you also see 2 points, point A and point B. Point A is called critical point. For carbon dioxide, it's 31 Celsius and 73 atm, very high temperature pressure. What does this mean? Meaning, at this critical point and beyond, the density of your liquid and gas phase becomes equal. You no longer can distinguish liquid and gas at this point and beyond. You also have a point B. Point B, you call it triple point. For CO2 carbon dioxide, triple point is negative 57 Celsius at 5.1 atm. So this point refers to solid, liquid, and gas at equilibrium. You have three phases which are coexist. Your line 1, let me call this is line 1. This line called solid gas phase line. Along this line, you are going to observe sublimation and deposition, which occurs in the reverse direction. They reach the equilibrium. Also refers to the solid and the gas phases are in equilibrium. For this straight line, so your solid and the liquid phases are coexist or in equilibrium. So this line you call the solid-liquid phase line. What you are going to observe, melting and freezing, which are coexisting, occurring simultaneously. The very last line, this line between A and B, so this is called the liquid gas phase line, meaning your liquid and gas are reaching the equilibrium. You observe the vaporization and the condensation. Be careful for your CO2, this solid liquid phase line has a positive slope, meaning your solid carbon dioxide is higher than the liquid carbon dioxide. On the other hand, if you have the phase diagram for your water, so you also have three different regions. You have solid, liquid, and gas. You also have three phase lines. However, your solid liquid phase line, this straight line, you found you have a negative slope. This slant to the left. This line slants to the left. The reason is the liquid water is heavier than your solid water. Solid is less dense compared with liquid, meaning water expands when it's frozen. The density of liquid is bigger than the density of liquid for your water. Water is a special molecule. So that's what you need to be careful. And also remember one point, whenever we're talking about the freezing point and the boiling point of water, make sure that refers to the 1 atm. If you have a different pressure, the boiling point for water will be varying. So this is about the phase diagram for your solids, carbon dioxide and water molecules. And then we are going to discussing the different forces, such as bonding forces and the non-bonding forces. I'm going to stop over here. Next lecture, we are going to discussing this bonding and the non-bonding forces. So what is the force? And do we have a model? If you have the model, what will be the basis of attraction? And how high the energy is? What is the commonly used examples? So also for the non-bonding forces, we are going to study I think it's six different types. And what's the model, and what's the basis of the attraction for each type of intermolecular forces. Also how high the energy could be, and the examples. And then we are going to study each of the different forces in detail and some examples, such as hydrogen bonds, such as boiling point, melting point influenced by the hydrogen bonds. And then we are going to predict the different properties of those molecules. Then we learned a little more about polarizability and the induced dipole forces. So that's related to your last intermolecular forces called London dispersion. London dispersion forces. Also, we are going to do some practice. So essentially, that's what I want to show you for today.